I'm tomorrow here. My flight is tomorrow 8 p.m.
Oh, you're tomorrow night you're leaving?
Yeah,
okay.
So tomorrow morning comes to him.
Hi, so let's get started. So our speaker today is Anze Slosar of Brookhaven National Laboratory, and we'll be telling us about Lyman-alpha forest with BOSS.
Okay, thank you very much. I'm very glad to be here. Last time I visited CITA was 6 years ago, and things haven't really changed that much. Well, yeah, some people are still here. And I'm going to talk about Lyman-alpha forest with BOSS, which is a new experiment that tries to measure a lot of QSO sightlines. So I must say that coming to CITA, it's a bit of a problem, because I work essentially at two things these days. One is non-Gaussianity, and you have Neil Dalal here, who is basically an expert on non-Gaussianities, and the other is Lyman-alpha forest. So you can always ask Pat about it, right? So it's really, it's not very useful to invite me, because you've got local experts for things I mostly work about. So I decided I'm going to talk about Lyman-alpha forest in particular because I've been trying to work on Lyman-alpha forest with the BOSS experiment. So let me start with a very simple observation. That essentially, if you think about what we do in cosmology, in most cases we measure two-point functions. Okay, so apart from measuring the expansion history directly to things like supernova, where the attacks are like standard candles and so on, the second thing you do, you measure, you're given a field, and your jerk reaction is to measure its two-point function, which can be either a power spectrum for CMB or galaxies, or it can be essentially a correlation function, for example, like BAO. And from signal to noise, this actually makes a lot of sense, because for given any field, you can measure the one-point function the best, which is mean, and the second thing you can usually measure very well is the two-point function. And therefore, we can link these two-point function measurements we do from various traces of structure to the underlying theory, which gives us the predictions based on linear theory and then later extensions. So to measure two-point function, to be able to do cosmology, you need the tracers of underlying matter. And here's a bunch of tracers which we know of as a function of redshift. So this is low redshift, this is high redshift. Of course, we have CMB, which is a redshift 1200, so it's way down there. But this is essentially the low redshift universe that you can do. And these are different the different samples we use to measure, to trace the underlying matter density. So you can start with something like SDSS main galaxy sample, which only goes to like 0.3 in redshift, and then SDSS LRGs goes to 0.7 in redshift. Then BOSS LRGs essentially will go, well, this is already big BOSS LRG, but you can push LRGs down to 1, right, with future experiments. BOSS will still go only to around 0.7 in redshift. And then if you want to go much beyond 1, we're talking about really big experiments. For example, the big BOSS emission line sample, we only go to redshift around 2. And if you look at the Lyman-alpha emitters that JDEM wants to do, they only also go up to redshift of 2, you know? And if you look at things like SDSS quasars, which are bright enough to do, say, clustering analysis with them and things like that, then you can push a little bit over 2, but this becomes very hard, very expensive if you want to push very hard. Then, of course, you have a third expert here, Li Pen, who works on 21 centimeter, and this, in principle, can allow to push to much higher redshifts. So you can, there are essentially two modes in which we can measure these things. One of them are essentially high redshift. Redshift is bigger than CIF, roughly before ionization. We're essentially seeing the neutral gas that emits 21 centimeter spin flip transition. And the universe ionizes, and then things become hard, but maybe you can see the 21 centimeter emission again at low redshift, where essentially you simply look at the integrated line from individual galaxies, right? When these galaxies are bright enough. But people will typically talk with this low redshift version up to redshift 3 or something like that, 2.5, 3, and high redshift versions beyond 6. So really, if you want to do something between 2 and 3 and 4, there's not much left, right? So Lyman-alpha forest is, I think at the moment, pretty much the only reliable tracer that allows us to trace dark matter fluctuations at this redshift. I'll go into what Lyman-alpha is briefly now. So what's the basic idea? The basic idea is that you have a quasar that has a Lyman-alpha emission line, which you can usually very clearly see. And then as the light from quasars travels from quasars towards us, it gets redshifted due to expansion of the universe. And then as it hits the clouds of neutral hydrogen, these clouds absorb some light and absorb exactly the frequency which corresponds to the Lyman-alpha frequency at their own rest frame. Okay, so clouds which are very close to the actually quasars, which absorb just a little bit blue worth of Lyman-alpha emission, and clouds which are closer to us will absorb very much blue worth of Lyman-alpha emission. So the basic idea then is you look at the quasar, you have line of sight. Line of sight will go through some sort of neutral hydrogen. And then this emission, absorptions in the spectrum, blue worth of Lyman-alpha emission, actually tell you something about the structure along the line of sight. And this cartoonish picture actually works very well in reality. These are two real spectra of real quasars. This is a low redshift quasar and a high redshift quasar. And you can see at high redshift, essentially, there is more neutral hydrogen, so this forest, these fluctuations I talked about become much more pronounced and contain a lot of information. While if you look at the low redshift quasar, essentially all the intergalactic medium is ionized, so you get very little force. You get a couple of absorption systems. And of course, one quasar gives you information about one line of sight, but then you can combine many of such quasars to push statistics and get information get three-dimensional information. So why we think Lyman-alpha force is good? So the first thing is that line of sight goes through typical parts of the universe, and I think this is very important to stress, because the other traces which you use are essentially galaxies, and galaxies live in rare peaks of the underlying field. So they're special parts of the universe, and to make a galaxy glow involves a lot of complicated nonlinear astrophysics. While the typical line of sight of quasars simply goes through typical parts of the universe, which are only weakly nonlinear and therefore much easier to calculate from first principles. It involves much higher redshift than galaxies, and the fact is that each quasar essentially gives you main information points, right? So if you use a galaxy as a tracer of underlying field, each galaxy gives you basically a bit of information about density at that position, while here we get information along the line of sight between Lyman-alpha and Lyman-beta. And essentially, the rest frame systematics can be dealt with in a statistical manner if you have enough of these quasars, right? And what people most commonly argue against Lyman-alpha is that it's all about, physics, hydrodynamics, and shocks, and so on. At the scales we're talking about, these things are really not important, right? I mean, they're not majorly important, and they can be, I mean, even rough modeling with some parameters to marginalize over usually, it's good enough. So what's the history of Lyman-alpha forest? So in the past, even before 1998, people said that there was no measurable correlation on scales bigger than 1 megaparsec. And the reason was that in the past, people thought of these absorbers as being essentially individual objects that have not completely decoupled from the universe, and essentially they're just randomly scattered to the universe, and they absorb this light. Now, in 10 years, the field has progressed amazingly. So already in 1998, there was the claim by Rausch in Astronomy Reviews that maybe there is a weak clustering. And then to 2003, Martin White, in a new crazy, essentially, conference proceeding, proposes doing baryonic acoustic oscillations with Lyman-alpha, which at the time sounded like completely wacko. But then in 2006, Patrick published flux power spectrum from SDSS. And then in 2007, Patrick and Daniel Einstein claimed that you can actually measure distances to redshift of 2.5 with 1%. And in 2009, we actually have BOSS experiment, which is trying to exactly measure baryonic acoustic oscillations with Lyman-alpha. So we went from 98, when people believed there is absolutely nothing in there, to crazy idea in 2003 to actually do with Lyman-alpha, essentially spending $50 million to try to do it in 2009. So the progress has been quite amazing. So however, let's try to understand what we really measure, right? So the thing is that with the picture I gave you before, it's clear that what Lyman-alpha forest measures, it measures the density of neutral hydrogen, okay? So what has density of neutral hydrogen to do with underlying dark matter fluctuations? There are some important papers by Gnedin and Hui which actually just explain these things simple, try to get an intuition for what's happening. And essentially, the first thing to understand is what are baryons. How are baryons responding to the dark matter fluctuations? So if you simply write evolution equations for baryons, how the perturbations in baryons, well, in dark matter and baryons grow, you get exactly the same equations. You get coupled, they both contribute to the force, right? And this is essentially Newton's law in expanding universe. However, for baryons, you also get this extra term. And this extra term corresponds to pressure on small scales. So if you take a cloud of dark matter and collapse it, it will say okay. If you try to do the same with baryons, there will be pressure that will try to oppose this thing and essentially smooth out fluctuations on small scales. So if you look at the large scales, baryons essentially follow dark matter. But if you look at small scales, pressure suppresses fluctuations on scales smaller than gene scales. And these are just some plots showing how this works. So this is K corresponding, a couple of hundreds kiloparsecs and so on. And this is the ratio of the baryon fluctuations to dark matter fluctuations. So baryons trace dark matter on large scales, but then they have very little structure on small scales. And then the exact precise amount of filtering depends on the thermal history of the intergalactic medium. So once you know what baryons do, you can actually calculate how much neutral hydrogen you have via some sort of very simple prescription, assuming that neutral hydrogen and are in photoionization equilibrium. In other words, the amount of recombinations exactly balances the amount of photoionizing photons floating around. And because the recombination is proportional to the square of the local density, it's a two-body process, you get that the amount of neutral hydrogen is roughly proportional to the rho squared. But in fact, this recombination coefficient has some temperature dependence. So you see that essentially the number of neutral hydrogens and therefore optical depth goes as roughly 1 plus delta, where delta is dark matter delta, to 1.7. So, well, this doesn't switch off anymore. So to zeroth order, you can see that what you measure flux is e to the minus tau, and just some sort of very complicated transformation of the underlying dark matter field on large scales. On small scales, things become more complicated. But the way to think about what you really measure lambda forest is you measure some sort of very nonlinear transformation of the underlying field, which would then have the same large scale properties.
You're measuring delta here on the gene scale. That's the scale which you're doing everything.
Yeah, I mean, this is slightly hand wavy. That doesn't work exactly. I mean, you can't just say that tau, because this is only transformation. You can't just say tau, flux on large scales is exactly this thing when this is delta L. You do this on some sort of small scale, which is bigger than gene scale, right? And then you essentially have to. I mean, there will be some effective bias with which flux traces dark matter on large scales. So this is how Lyman-alpha forest works, and I'll talk a little bit about BOSS, and BOSS is this experiment which we try to use to do to measure Lyman-alpha forest. It's one of the 4 experiments which are composing SDSS 3. So SDSS 1 and 2 were extremely successful, and now we have SDSS 3. And BOSS is actually a spectrograph, which is 1/4 of the SDSS 3. It uses a 2.5 meter SDSS telescope on Apache Point Observatory. Here's a telescope. It has a big building that actually goes over the telescope to enclose it. It's essentially a 1,000 fiber spectrograph with an R of around 2,000 and has wavelength coverage between 3,600 and 1,000 nanometers, right? So you can, essentially, it's a refurbished SDSS spectrograph, right? It has slightly better resolution, better sensitivity, and slightly better wavelength coverage. It goes deeper into blue, which means we can actually see more Lyman-alpha forest. And essentially, it's a 5-year survey. So the plan of the entire project is to measure spectra of about 1 million LRGs and about 160,000 quasars with some sort of usable forest. And the reason why I want to do is to use tracers, these tracers, LRGs and QSOs, like Lyman-alpha forest, to do BAO measurements. And we try to do this over 10,000 square degrees. So commissioning was from August 2009, so the thing is operating for nearly a year now, and we're starting taking science data from December 2009. So this is how the back end of the telescope looks like. So I mean, you can't see this very well. So essentially, you got three degree focal plane, and on this focal plane, you either put a camera, which you store into this doghouse if you don't use it, or you can put some slits, fibers on a fiber cartridge, which you then plug into these spectrographs, which sit at the edge of the telescope. And this is essentially how these things are. So this goes into focal plane. So here you have a big piece of metal which holds directly into it, and then you take fibers, and these fibers actually are at the positions of galaxies in the field, and then the light goes through here and then to one of the two spectrographs. They're identical, only each one has about 500 fibers, and the light goes in, it gets split by dichroic, then you have some gratings, and then you have a blue camera and a red camera. So this is red camera, and this is blue camera. And this is essentially how it works. So this is the janitor of the APO, which has been promoted into fiber plugger. So as you can imagine, this is very painful. Trying to plug thousands of fibers, all day long. This is what he does. And this is actually the first light from the telescope. So this is actually the first light from the telescope, and you can see this is essentially stellar spectra. This is spectra. This is the wavelength direction, and these are different fibers. And this was in end of August 2009. These are the more reasonable recent image. One of the galaxies, one of the QSO. And David Schlegel calls this a noisy data survey. And the reason is that the data really, the signal to noise is not extremely good. Compared to SDSS, we have 160,000 quasars, whereabouts SDSS has only about 50,000 quasars with spectra. But essentially, signal to noise, it's a bit worse. That's because we go deeper and take images of many more faint spectra. So the fact that we go fainter than we go actually into fainter spectra, which are fainter than improving the signal to noise from new CCDs. So the data are quite noisy. It turns out that for Lyman-alpha forest, this is what you want to do, because whenever you do some sort of predictions of how you're going to run this experiment, it turns out that predictions always tell you go for more spectra rather than more signal to noise. Okay, and that's why this is okay. Of course, you still need to have spectra which are for good enough quality so you can actually measure Lyman-alpha. I mean, you can see it's a quasar, right? So this is the footprint of the experiment. This is the North Galactic Cap, which is essentially the old SDSS footprint, and there was extra imaging done on the South Galactic Cap. So we have about nearly 8,000 degrees from SDSS1, and we have 1,500 more on the South Galactic Cap. And the idea is to fill in both caps to get around 10,000 square degrees altogether. So what we want to do with this data essentially then is to measure the baryonic acoustic oscillations with it. So let me just spend 2 slides on baryonic acoustic oscillations. So the idea is that before recombination, the primordial plasma can support acoustic waves, right? So so as a certain mode enter into horizon in primordial plasma, it starts oscillating, essentially propagating sound waves, as this movie from Daniel Eisenstein shows. And then as the CMB is formed, as the photons decouple from baryons, this acoustic wave gets frozen into the underlying plasma. So essentially, the signature of this is a peak correlation function at a distance which corresponds to the amount of how much sound waves have traveled since between the mode entry horizon and between mode decoupling, like baryons and light decoupling. So the way this looks like with galaxies, essentially, is that the correlation function of galaxies has a peak at around 100 megaparsecs. So if I look at the number of galaxies around each given galaxies and compare them to how many you expect them if the distribution of galaxies is random, there is excess compared to slightly smaller and slightly larger distances at around 100 megaparsecs. And this is actually a characteristic scale which acts as a standard ruler. This is the BAO detecting for LRGs from quite a couple of years ago. It's a first convincing detection, but it's still it's very pretty because you can actually, it was measured in Fourier space, so you can see this nice bump at around 100 megaparsecs inverged. And then if you do this in slices of redshift, you actually have a standard draw that allows you to measure the distance to given redshifts as a function of redshift. So this is done with galaxy, but has never been done with Lyman-alpha forest. So you can do simulations of Lyman-alpha forest. Ideally, you do hydro simulations. What we did was something much easier. We just take dark matter simulations and use the FGPA, which is like fluctuating Gunn-Peterson approximation, to convert delta into flux. This essentially is what I said before, this complicated nonlinear transformation. And what it shows, not surprisingly, that flux correlation function follows has the same shape as dark matter correlation function. So you do expect to get a peak at around 100 and a little bit of megaparsecs. And this is real space and redshift space. And if you then divide this correlation function by what you expect from the dark matter linear correlation function, you essentially get nothing strange. Essentially, it's absolutely flat. Okay, so essentially the bias of flux at very large scales is to zero order of unknown quantity, but it's essentially it's constant, right? Which is very encouraging. So it means that essentially, if you see this bump, then you should be okay. And if you ask Pat McDonald, he will tell you that this is not really surprising, and I agree. Essentially, any transformation will give you a local bias on large scales. We also looked at the redshift space distortions, and here again, so this is the redshift space distortions. This is real space for dark matter. You essentially see this is radial direction, this is transversal direction, this is correlation function. This quarter of a ring essentially is the baryonic acoustic feature at 100 megaparsec. And then if you go from real space to redshift space, you get this transformation, right? So it gets much more, you get many more, why do that direction? Okay, so this is a parallel, you get Kaiser squashing of these contours. And if you compare this visually, what you expect for linear field, so this is the dark matter only field with Kaiser prediction, it just looks visually very similar, right? It's quite clear that the Kaiser is a very good approximation of what's going on. And if you compare this is for flux, the same picture for flux, and you get exactly the same picture for flux. So not only in real space, also in redshift space, simply you can think of the flux correlation function as being tracing the linear dark matter field with some sort of effective beta and effective bias on very large scales.
When you said they are exactly the same, how much difference are you actually talking about?
Sorry?
You said they are exactly the same.
Yeah. I mean, it's very hard to actually get to calculate chi-square in a robust manner, right? So I've tried a little bit, and I couldn't get with the number that would really believe saying, are they statistically the same given the uncertainty in measuring these things? And the reason is that these are simply simulations, and if you do simple things, you cannot see the difference between, on these scales between beta Kaiser compression and nothing.
But the Kaiser effect should not change the position of the peaks.
Sorry?
Kaiser effect does not change the position of the peaks, the baryons.
No. Linear theory, no. Linear theory, the monopole essentially is just amplified version of the unredshift monopole. Now, in this paper, actually, we claimed that the beta for the flux is exactly the same as beta for dark matter, which I think it's not true. I've convinced myself that this happened to be here the number by fluke, okay? But in reality, I think the beta, the parameter that controls how much squashing you get from Kaiser is in general different from that for dark matter. Okay, for dark matter, essentially just f, and for this thing is f over some effective bias. Okay, so in principle you should fit for these numbers, but there is, I mean, surprise, there's nothing strange happening here. And in principle you can test this approximation because Kaiser effect goes from having monopole only to having monopole plus quadrupole plus hexadecapole, whatever, and higher moment should go to 0. So this gives you some hint in understanding whether this really works or not. Right? And there are some consistency relations.
But the forest doesn't have any fingers of God, I guess. Right?
Forest doesn't have fingers got, but also what we do in practice. Well, okay, it has, yeah.
I mean, not like beautiful, but
The forest should avoid virialized objects like that, right?
just small.
Oh.
No, but I mean, what we will do with this thing, we'll simply chuck away the nearly parallel paths, right? We throw away pairs which are from the same quasar. I think this is the safest thing. Conservatively, if I don't want to deal with power due to self fluctuations, I would simply only calculate collection function by having pairs. So then, unless you have pairs which are very, 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 very close together, then you're not going to see this thing. But you can see it if you measure small scale power spectrum, right? But see, fingers of God actually would give you everything, right? They've just amplified the power all over the place.
It's not like a cluster. It's not.
Because you're cross correlating different quasars to avoid
To
noise from a single quasar.
yeah, for
This is the idea.
yeah, because yeah, continued fluctuations have to cancel from quasar to quasar, right? The question is how fast will they cancel, but they have to cancel if they're random from quasar to quasar. But otherwise, I think on any given quasar they will add power. That's what I want to avoid. So the forecasting how well you can do by trying. All these papers actually somewhat simplistic show that there are no hidden surprises. Everything works roughly within noise to the way you expect it to work. But actually forecast how well you can do with future surveys is hard. And this is from figure from Pat and Eisenstein in 2007, in which essentially forecast that if you go to 22.5 in G magnitude, you can reach about 1.5% fraction error on scale on the distance to the redshift of to the redshift for relevant Lyman-alpha forest. And this is then our official goal of BOSS. I mean, the question whether we'll reach it or not, it's a different one, but these are numbers we're talking about. They're really quite impressive. So now that we have BOSS, that it's taking real data, let's try to actually do it, right? And the first thing is actually trying to get targets from data. And target selection is essentially done by 3 different methods and a bunch of people. It turns out to be much more difficult than I expected it to be. The fiber budget is about 40 fibers per square degree. And initially we hoped for around 20 QSOs per square degree to have about 50% efficiencies in selecting targets. But I think essentially we will end up getting just something around 16 quasars per square degree. But of course, not every quasar is worth the same, right? So this is the quasars. This is the so-called another product by Pat. It's called the value of a given quasar. So if somebody gives you a quasar at a certain redshift and certain magnitude, this tells you how much this quasar helps you in measuring BAO with Lyman-alpha forest. And of course, as you go to fainter quasars, they become less helpful. And as you go to low redshift quasars, so most of the forest is outside the spectrograph, they become less useful. So there is a sweet spot between 2.5 and 3, roughly, right? So you want to pick bright quasars between 2.5 and 3, ideally. Now I'll show you a movie why this is hard. So this is a movie from now, showing like one color selection, U minus G versus G minus R. So this is the quasar spectrum going through the bands. And this is how it appears on this plot. You see it dances around. But precisely between 2.5 and 3, where you want to select quasars, it goes through stellar locus, okay? So it's unfortunate, you know, that it doesn't, that it actually has very similar colors to stars in this region. You can find different combination of colors which will work better. This is I minus Z versus R minus I. And here's between 2.5 and 3, it's somewhat distinct. So if you have very good photometry, in principle, this is something you can distinguish between quasars and stars if you try hard. Now, this is a couple of slides from Myers, which tells you that this actually is very hard. So this is again U minus G, G minus R, where the stars live. And these are quasars with redshift bigger than 2.2, the targets you want to do. Yeah. So these are the quasars. This is the way the quasars would live with respect to stellar locus if you had no noise in your survey, right? And here you can see you could, in principle, cut things properly, right, and get stuff out. The problem is that when you have photometry errors, the things spread up all over the place. Okay, so these are the same quasars to which random errors were added, consistent with what photometry we can get at low redshift, and it turns out that things go all over the place. And I think this is why we're getting lower efficiency than we hoped for. If you take at our targets around stripe 82, we really do have a target selection efficiency of around 50%. But when you go away from stripe 82, when you have only single epoch photometry, then things do get considerably more messy. Okay. So at the end, we chose, and we will have actually have two samples. One with the core sample, and the idea is you want to have a fixed algorithm that selects quasars, and it's fixed for the entire survey. It doesn't have to be the best ever, but it picks up the first 20 fibers per square degree, and has a well-understood selection function, and you want to use this for quasar science. And it's calibrated to give roughly 20 per square degree in average. But of course, when you get closer to the galaxy, when you have many more stars, these things blow up. And then on top of the core sample, we have the so-called bonus sample, which uses any extra fibers you have between whatever these guys uses and 40. And this is like a free market. You can try any kind of wacko idea as long as it gives you quasars, right? The idea is that all these extra quasars will be used only for Lyman-alpha forest work, so you don't even ever hope to use them for any quasar science work. So how you go about doing this? I said we had three algorithms. The simplest is the so-called K. I mean, I want to show you this just to tell you how much work has gone for so little effect. The easiest thing is the so-called KD plus chi squared, in which you essentially take you take a training sample of quasars, a training sample by stars, and then you put them in these histograms in these colors, and then essentially you have some sort of a kernel that smoothes this distribution and essentially tells you if I have again an even object, I mean, where does it sit on this thing? Are with this, in this smoothed probability histograms, are there more quasars or stars around? And then decide it whether it should call something a quasar or star. And then has a lot of things bolted on, something like hodgepodge chi-square distance from a set of model stars to keep it away from the locus. Okay? So it's some very complicated Chomsky procedure, which actually works reasonably well, but has the main disadvantage that it can't do errors. And the second method which was proposed by David Schlegel, and I think it's actually extremely simple, extremely elegant, is essentially saying, okay, I will have a catalog of stars, and I will have a catalog of quasars, and I know what my photometric errors are. Okay, so what you really write down in terms of in probabilistic sense is saying, if somebody is giving me an object, right, and I know this object was randomly selected from one of the objects in the catalogs, is it more likely coming from the catalog of stars or catalog of QSOs, right? And in terms when these catalogs become very, very deep, when you have a lot of objects in these catalogs, then essentially they approximate the full Bayesian probability. Okay? As I said, the caveat is if you have deep enough catalogs, which you don't.
Your sampling of the different points is uniform. It is not uniform in the specific bias probabilities, right?
Yeah, so you want to have uniform sampling of quasars and stars. But up to a certain limiting magnitude, which we try to use. So that's why you go to stripe 82 when you have very deep imaging. Essentially, you picked up everything there, right? But if you read this expression, what they say, right, is so assuming one of my objects was exactly one of the guys in this catalog, right? Then what's the probability it belongs to QSO hat or the star hat? And it seems to work quite well. So then we have the third method was invented by French, is simply using the neural net, in which it's completely opaque. You create this neural net. You have this activation function. Something comes in, something comes out, right? And you don't care what it does, right? And then you train it again on some sort of sample of stars and QSO. But the funny thing is that what they did, which I think it's even bizarre. So the input are 4 colors plus G band magnitude, right? And then plus magnitude errors. Okay, so they treated errors instead of like fiddling with input colors consistent with errors, they just treated errors as extra input to the thing, and just retrained this huge network. But all in all, it actually works surprisingly well. So, but then people couldn't agree which method to use, right? Which one is better? Because if you use different metrics, different methods would appear to be better. These are the so-called heat maps saying how much different methods blow up close to the galaxy. The galaxy is here, right? And you don't want method to be really, really sensitive to how far from galaxies you are. So this political consensus at the end ended up being taking 3 methods, KDE, likelihood, and neural network, and then combine them with another neural net to get the final answer, right? And this essentially, this hodgepodge gives you, it's actually at the end surprisingly effective at selecting quasars, although only maybe a quasar per square degree or something like that more effective than any individual one. So the idea is for core, we now use likelihood, and for this crazy bonus sample, we just use all these methods again combined with neural net. But anyway, so we're struggling here, we're getting quasars. So what do you do with these quasars then? This is the average quasar spectrum you get from 4,800 Bose QSOs. And it tells you that, like, all in all, the telescope works amazingly well, okay? So you can see this is the Lyman-alpha line, this is the Lyman-beta, this is the Lyman-alpha forest. We try to use between these 2 emission lines to have the more Lyman series. And then you have all these lines, carbon 4, silicon 4, helium 2, carbon 3, magnesium. You have all these lines, and some of them I don't even know what they are, right? But it's amazing that, like, when you combine all these noisy spectra, you still get very, very nice composite spectrum. And some of the data still have issues. Some of the spectra are nice. This is example of nice spectrum giving a typical signal to noise that we see on these quasars. But some of them are just strange, right? You can find quasars which have funny, reduction artifacts when things go negative, or even if you look at the quasars, like quasars we had repeated observations using on different plates, you can compare and see how well does the noise work. In some quasars it works amazingly well. So this is the same. The red and blue is the same quasars observed with 2 different plates on 2 different nights, and you simply take the difference and calculate what is the RMS scatter divided by the sum of the errors. You get something which is essentially the same with RMS of 1. With some quasars it doesn't work so well, though. So this is an example when the same quasars observed with 2 different plates and 2 different equations, and you see the answer just has this huge photometric error, essentially just a slope in your things. And I'm being told that part of this slope is simply the fact that some fibers, when you put the fibers far away from the center of the focal plane, simply the optics will change how light focuses. So these things are apparently very hard to calibrate out. So these are some of the things we essentially will have to live with. But in addition, even when telescopes function so very, very well, you've got various different things. So this is another quasar. This is the Lyman-alpha forest here. This is the Lyman-alpha emission. And you have the so-called damped Lyman-alpha system. These are just systems in which the column density is very high. And essentially, they have these broad wings here. You can see around 0. And you want to mask these things out. And there are several ways how to do this optimally. And then you have the so-called BAL quasars, which just are broad absorption line quasars, which you have essentially something is going with quasar fine. So they have all these features. And this is again a quasars which you don't want to use because you don't really know what's going on with quasars like this. So as you see, from data to actually getting something useful, it's a long way. So how are you going to analyze this Lyman-alpha forest? Okay. So you get the data, you get rid of dodgy ones, you mark bad pixels, you do this, you fit continuum, blah blah blah, and then you end up with estimates of the delta flux, which now follow this peculiar geometry, right? So you have these lines of sight towards you, and then each line of sight you have a region between Lyman-alpha and Lyman-beta where you have some points, right, telling you what is your estimate of delta f at this point. And then what you're trying to do is trying to measure the correlation function. And what turns out is, this is again from paper by McDonald and Eisenstein, is that if you want to optimally weight, you need to measure the small-scale correlations concurrently with large-scale correlations. Okay, so it's not like what you naively think that it doesn't matter that these points are close together, right? Actually, this changes pictures completely, right? And the reason to understand this is say the small-scale correlations are so large that essentially these 2 points are fully correlated. If this is the case, then essentially you just measure 1 point. You haven't measured 2. Okay. But if the correlation function between this point and that point drops to 0, you now have essentially 2 independent measurements, right? So your covariance matrix has completely different properties depending on what are the correlation properties between these points on small scale. Okay. So in other words, when you try to do the C-inverse weighting, whenever you take your data, you do C to the -1 data. What C to the -1 will be dominated by small scale correlations, and you have plenty of pairs that are sensitive to these things. And this appears in this in the power you measure as essentially projected 1D flux power. And then besides this, you have a lot of points, right? So with the present like 1 megaparsec pixels, this is 40,800, not 48,000. We already have about 600,000 points, right? So if you want to do this optimally, you have to start inverting, 6, 10 to the 5 matrices, right? And this is only about 5,000 quasars, not even we will have 160,000. And then, then you say, okay, but maybe I can do radial smoothing, okay? I'm just going to smooth along the line of sight and have more coarse pixels. But actually, these things do non-trivial things. They don't do anything to large-scale correlations, but they do non-trivial things to small-scale correlations, which are which are important, right? So I think the idea is that eventually we will use the optimal quadratic estimator to try to measure this. But at the moment we're not there, so we're just using trivial estimator, essentially just multiplying fluxes on pairs in bins. But we do weight by 1 over noise plus signal. So at least we do some very rough weighting with signal to noise. And this is where we stand at the moment. This is 4,800 quasars from BOSS. And this is the measurement correlation function, the ratio of 2.5, still fairly crude initial analysis. And the amazing thing is that, so this is now correlation function not multiplied by r squared, okay? So what you're usually used to seeing is correlation function multiplied by r squared, so you see this nice bump. I didn't multiply by r squared, so there is no bump here, right? And these points are very heavily correlated, so it's essentially consistent with 0 down here. But here, at the small separations between 5 and 35, we clearly see some signal. And I think this is pure lag, but this blue line was predictions from our paper, how the signals will scale at small scales. And there was no fudge. I mean, I think this prediction is accurate only about 2 to 50%, but for us, it actually worked very well. You see, I mean, these points essentially bang on the blue line. And these are the errors from jackknife. And the significance of detection of cross-correlation at scales bigger than 5 megaparsecs is around 1.6 sigma. So we are still very, very far away from actually seeing something around 100 megaparsecs. And these errors are still a bit too big given the projections. But I think at least something not massively wrong is happening when you have 5,000 quasars. So does it really matter? Okay, so this is my controversial slide, and I think no, right? If you think about it, there's not really not much motivation to measure BAO at large redshift, because even if W is not -1, say you have some dark energy which is not lambda, it says W is minus 0.995. The universe is still most likely isolated at high redshift. Okay. And if it's ice in the sitter, you're going to get what you expect from ice in the sitter. Essentially, you're not really learning anything new. So the only reason we could actually see something non-trivial was that W was not just -1, but it would be something, completely different.
It's a flat universe.
Okay. What is that?
So curvature, for example, can you measure using combinations of highs and lows?
Yeah, but no, curvature is measured using CMB, right?
Well, I mean, but there's still like some error on the curvature, and then having this, I think, really beats that error.
Well, okay. Can you beat Planck measurements, distance to redshift?
This is patched complaint, not mine.
Okay, no. Okay. Okay. But really, I think, okay, so A, you don't expect W to be but really, W is -1, okay? I'm fairly convinced about this, right? And the reason why W must be -1, and if you talk to theoretical physicists, they're fairly convinced this is the case, is if you take any fundamental theory, there is no symmetry that would protect vacuum energy from being away non-zero, right? And even if such symmetry existed, it would probably operate in more symmetric state rather than less symmetric state. And we know that in standard theories, universe has gone through several phase transitions, and the vacuum energy can only go down, right? So if it's 0 now, it must have been non-zero in some sort of more symmetric state, which sounds just crazy, right? And I know there are ways to go around it, all this funny mechanism, but I think that they sound very, very contrived, okay? So the reason why I'm doing BAO with Lyman-alpha is not because I believe in dark energy, but because I believe this is a good way to convince people that Lyman-alpha works. And I think...
The one place where you know the universe will believe, anybody who believes in inflation believes in a lambda-dominated universe where W was -1 plus epsilon, where epsilon is a slow old parameter.
Yeah, okay, but the inflation had to end, right?
Yeah, and ours will end in 60 epochs from today. It will end again, but that's a long ways for your lifetime at least. Or mine.
Sorry?
Even the same.
Yeah. I mean, inflation really cooled down universe as well, and then you have overheating. I don't know. I just Yeah, okay. This is not crucial. All my point is I think you can do much more exciting things with Lyman-alpha than simply measuring BIO. And I'll finish in 2-3 slides. So one thing is this claim by Dalal, this famous paper that you can measure non-QSO of the local type that induces a scale-dependent bias in traces of structure. You see here. Dalal disagrees with this, but we're checking this. We have some preliminary results showing that the same effect is true in Lyman-alpha forest for FNL of 100 and minus 100, okay, in real and virtual spaces. So this was, again, this would imply measuring very, very large scales with Lyman-alpha forest and the continued fluctuations that I saw and so on. It's not clear where it's going to work. The other thing, of course, is you can measure radical spectral index, which I think if you measure small-scale power spectrum and try to measure the radical spectral index, this could work very well. And I think this is very important because WMAP7 has finally detected the spectral index to be less than 1 or bigger than 3 sigma, and you expect the running to go square of this thing. So with 3,000 quasars, we already have 0.01 limit on running. So I think with an order more magnitude of quasars, we should detect it, right? And data for neutrinos, right? We know that we have the lower limit on the sum of the mass of neutrinos from terrestrial experiments to be bigger than 0.05. And I think the small-scale Lyman-alpha forest has the ability to measure this on large scales, has the ability to measure, to have, at least on paper, sensitivity to either detect this or see something that's very strange. And I have 2 slides on library systematics, but I don't have time to go through them, so just finish here. So what?
Yeah, okay, well, right. Like, so is the effect mainly changing the shape of the power spectrum?
It's changing the amplitude. Okay. So for this file, so if you go to neutrinos that lie, the scale at which the free streaming length is very large. Okay. Right. So it's unlikely you're going to see this with Lyman-alpha. What you can do is you measure, essentially do what Pat did with small scale power spectrum. Simply just measure the small scale power spectrum, calibrate it on hydro simulations, which then gives you essentially sigma 8 at a redshift of 3, which then allows you to see a decrease in amplitude due to neutrinos.
But you have to believe the actual amplitude you're measuring with the forest power spectrum.
Yeah. I mean, I'm not saying it's trivial, but at least on a statistical sense, the signal should definitely be there. Okay, by some sort of large margin. And the universe also, the good thing is the universe is much more linear at redshift of 3, okay? So these features have not been erased so much at the redshift of 0. So you can look at 1 megaparsec, and the universe it's only weakly linear. So this information should be there.
What's the effect, I guess, is also redshift dependent, right? Could you like redshift dependence?
You mean because neutrinos free stream?
Yeah, right.
Well, I think this will be very, very hard because neutrinos. I mean, even if you believe neutrinos are this light, they become non-relativistic at redshift of 30, 50, right? So yeah, you always have tail. You have tail which are also relativistic, but this tail is it's rather small. So I mean, yeah. I mean, there was a recent paper in which people finally managed to have embodied simulations with neutrinos in them, right? And I haven't managed to read it, but I think this question will be answered whether they have any effect.